So, now we can move forward. As I said, we will use renewal reward techniques, which we are somewhat familiar with. So, I will not spend too much time on this. So, let me develop some notation, right. So, we will derive. So, we want to, what we want to do is to derive steady state probabilities using renewal theory, just like we did it for DTMCs, right. This is one approach, there are other approaches as well. Okay, so I am going to denote, let us say I am going to keep x0 equal to I throughout. Okay. So, at time 0 the CTMC starts at state I, and I am going to say let mi of t be the number of state transitions made by the CTMC in the interval 0 t. Okay. And I am going to call mij of t as the number of transitions into state j in the interval 0 to t. Okay, starting in state I. So, to give you a picture, so this is time 0, all right, and that is time t. Okay. So, you starting at time 0 x naught is equal to I, right. Let us say the first transition u1 happens here. So, this is your S1, and then there is another, you get into some state, and then there will be an exponential corresponding to that state, then there will be some other state transition S2, S3 and so on, right. So, you look at up to and including t, what are the number of transitions that the CTMC has, the DTMC, the CTMC has made, right, which is also the number of transitions the underlying DTMC has made. In this case is 4, right. So, in this case mi of t will be 1, 2, 3, 4, right. And if let us say that here I entered state j and here I entered state j, here I entered some state L, here I entered some state k. Okay. So, this guy will be exponential nu L, this guy will be exponential nu j, that will be exponential nu I, that will be exponential nu k and so on, right. Now, mi j of t will be the total number of times I have entered state j until time t, which in this case will be 2, right. So, these two these are you can view mij of t and mi of t as some counting processes, right, it is counting something, right. What you will see is that this mij of t is actually a delayed renewal process. Mi of t is not a delayed renewal process, it is not a renewal process at all, because it enters different states and stays there for different time, but mij of t turns out to be a delayed renewal process. So, we have to see that, right. First of all, you can prove a few lemmas, okay, which I will not get into great detail. You can show that lemma 1, you can show that limit t tending to infinity, if you look at this limit t tending to infinity of mi of t, okay, this will be infinity with probability 1. Okay. The way to see that is, so the proof sketch, first show S1 is equal to U1, S2 equal to U1 plus U2, dot 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 Sn equal to U1 plus U2 plus dot 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 Un are all legitimate random variables, meaning that they are all finite with probability 1. Okay. So, for example, you can show that to show that if you look at this guy, probability some un is greater than u, right. This is simply the, what is the probability that un is greater than u. So, you have to so un will be an exponential with parameter some nu k, right. So, the probability of that will be like this. So, you have to go from I to k in n minus 1 steps, right. For underlying Markov chain should reach state k, and then you have an exponential, right, of rate nu k. So, you will have e to the minus nu k u, right, where k maybe I should say is equal to 1 to L limit L tending to infinity. Is that right? I am just summing over all possible states and taking limit L tends to infinity. Right. Maybe I should just write this. This is just an infinite summation, k is equal to 1 to infinity. So, if you send, maybe I should write this as just, this is easier. Okay. Now, you should look at limit u little u tends to infinity of probability u n greater than little u, you will get limit u tends to infinity sum over k equals 1 to infinity p I k n minus 1 e to the minus nu k u, right. Now, I can sum, maybe I should do this, right. I can sum to some finite limit u tends to infinity sum to k equals 1 to L p I k n minus 1 e to the minus nu k u plus the rest of the sum from L plus 1 to infinity, sorry, L plus 1 to infinity, I can have p I k n minus 1, and if I make, see, and then you have e to the minus nu k u, but that guy is less than or equal to 1, right. So, if I make that 1, I can make this less than or equal to, right. This is true for all L, it's true for all L, all right. Now, if you look at it, this term, so I have these two terms to handle, right. The first term is a finite sum, and as u tends to infinity, the first term goes to 0, right. So, this guy goes to 0 as u tends to infinity, and second term, its the second term is as goes to 0 as L becomes large, right. That is because it is a tail sum of a finite, all these p I k's n minus 1 sum to 1 after all, right. So, the second sum goes to 0 if you take a large enough L, right. So, bottom line is that if you just do this carefully, you can just conclude that u n is finite with probability 1, right. That implies for all n greater than or equal to 1, implies S n, which is simply sum over u m, is also finite with probability 1 for all n, right. S n is the epoch of the nth transition, which is we have just shown is a legitimate random variable. Okay. So, that is step 1. So, the first step is involves showing that all these ui's and therefore, the S n is finite with probability 1, they are legitimate random variables. Next, use the following equivalence, right. We know that the event Sn less than or equal to t is equal to the event that Mi of t is greater than or equal to n, right. For every sample path this is true, right. Now, so this is exactly now playing out like a corresponding result we proved for renewal processes, except this Mi of t is not a renewal process, but nevertheless this equivalence holds, right. And using this and the fact that Sn is a this Sn's are a legitimate random variable, right, which is finite with probability 1, then we can show that Mi of t goes to infinity with probability 1 as t goes to infinity. Okay. This I think if you go back and look at your lecture on the renewal processes, we use some continuity of probability sort of arguments and use the equivalence between Sn and n of t in the renewal process case to prove that n of t, the number of renewals, goes to infinity as t tends to infinity. A similar almost an identical argument can be used here to show that Mi of t goes to infinity as t goes to infinity. Okay. Next, so this number of transitions is going to infinity. Okay. The next thing you can show is that if you look at Mij of t, right, which is the number of start at x not equal to I and then you transition, right, into various states. So, let us say you get into state j. So, what did I draw? I think I drew, I am just redrawing the picture I had before. Yeah, so I am going to get into some different states L, J, K, J, whatever, right. So, I am here in state L, here in state J, state K, state J, and so on. Okay. Now, the issue is what am I going to show? I am going to show that these instances of entries to J constitute a delayed renewal process. So, you are going from I to J first and then J to J, right. These constitute a delayed renewal process. This needs a proof because see, if you may remember that in the DTMC case we said that successive entries to state j constitute a delayed renewal process starting at state I and we use the strong Markov property, right, to prove that successive entries to state j constitute renewal instances. Now, a similar argument can be used here. In fact, in the embedded DTMC, the successive entries to state j constitute renewal instances that we already know, and then the holding times are all independent across these successive intervals and dependent only on the current state, right. Using these two, we can show that Mij of t is indeed a delayed renewal process. So, this involves some kind of a proof in showing that the first entry times from from I to j, if you call that interval as some Tij and these intervals as maybe I should call it Wij and Wjj. These have to be shown to be finite in the first place, right. So, that also includes involves a little bit of an argument like I have done before. This is done in lemma, this lemma. So, this is in your book, this is lemma, maybe I should call it 721 in your book, and this is lemma 722 in your book. Mij of t t greater than or equal to 0 is a delayed renewal process for j not equal to I and an ordinary renewal process for j equal to I. Okay, so this proof you can it requires a proof. You can look at the book for arguing that all these intervals wij and wjj are finite with probability 1, and that these wjjs, the consecutive wjjs, are in fact identically distributed and independent. Okay, this comes from the strong Markov property of the underlying DTMC and the fact that the holding times are independent across these successive entries and also identically distributed because the distribution only depends on the current state. Okay. Okay, so this I will not spend class time in proving. So now I am going to look at the limiting. Now that I have a delayed renewal process, I can use some renewal reward arguments and look at the limiting fraction of time spent in state j, right. So I am going to look at the delayed renewal process mij of t. Okay. So here x not equal to I, and these are the instances where the Markov chain CTMC changes states, and let us say these are the places where the state j is entered, and these are all some other states k, l and so on. Does not matter, right. So my renewal instances are whenever I enter j, right. Now I am going to create a reward Rij of t whenever x of t equals j and 0 otherwise. Okay, this is my reward process. So I am in state j. So whenever I am in state j, I have a reward of 1. Okay, maybe I had another state here, m or whatever, right. So the process collects a reward at rate 1 whenever the process is in state j, right. Now I can say that the time average fraction of the fraction of time spent in state j is simply the time average reward, right, of this Rij of t, right. Now I know so I know this, right, limit, if I look at this guy Rij of tau limit t tends to infinity, this I know to be expected Rij, which is the expected reward in one renewal interval divided by the width of the renewal interval. I am going to call that expected Wjj, or let me just call it so as a matter of notation I am just going to call this Wj bar. Okay, Wj bar is the expected Wjj, which is the expected renewal duration. So that, you know, a duration like that, right, expectation of such a duration. Okay, this is true with probability 1. And what is expected Rij? What is the expected in one renewal interval? What is the expected time spent in state j? So that is, remember that this interval is exponential with parameter nu j, right. So the expected reward is simply 1 over nu j, because that is the expected value of that exponential, right. So the LHS is the average fraction of time spent by the CTMC in state j, right, starting in state I. right. So, I am going to call Pj of I, which is the fraction of time spent in state j given x naught equal to I, right, given that you started in I, right. So, Pj of I is your left hand side is equal to 1 over nu j w bar j with probability 1, right. So, what we see here is Pj of I is just, it does not depend on I at all, right. So, I can just call this Pj of I as Pj, right. We can drop I dependence, right, and then say that Pj, which is the average fraction of time spent in state j, is simply 1 over nu j wj sorry w bar of j. So, w bar of j is the expected renewal interval, right, and 1 over nu j is the expected amount of time spent in state j whenever you enter state j, right, in one renewal interval. So, Pj is this, alright, is almost surely. Excellent. So, this is a very nice result. Now, what about, so this is the time fraction, right, limit. Now, what about the ensemble average, probability of x t equals j given x of 0 equal to I, right. So, we have limit t tending to infinity, probability of x t equals j given x not equal to I is simply limit t tending to infinity expected Rij of t, right. The Rij of t is an indicator after all, it is just the expectation of the indicator that that the process is in state j, and this again is equal to by key renewal theorem, right. It is simply, the answer will be the same, the time average and the ensemble average will be the same, right. It will simply be nu j w bar of j, right, by key renewal theorem. In your book, I think it is 5108. Okay. So, what does this mean? So, the probability that I find myself in state j after a very long time having started in any state I is independent of state I and is equal to 1 over nu j w bar j. Okay. So, this is a very nice result. Now, this w bar j is not, we have to characterize it in terms of something that we understand about the process, right. So, we have, what have we established so far? So far we have established that the fraction of time spent in state j exists almost surely and is equal to 1 over nu j wj bar, and this is also the this Pj is also the steady state probability of being in state j after a very long time, right. So, maybe I should say, so this is equal to Pj, right, this guy is equal to Pj which is above, right. Now, but I want to find out this wj bar in more, in terms that I understand, in terms of possibly the nu i's and pij's or whatever, right. I want to characterize it in terms of the known parameters of the process. So, that is done as follows. This is an important theorem. So, consider CTMC with positive recurrent embedded chain and let pi j be the steady state probabilities of the embedded Markov chain. Let x naught equal to I be the starting state then with probability 1 the limiting time average of fraction of time spent in J is given by, I already stated the answer some time ago, right. So, Pj is equal to pi j over nu j over sum over pi k over nu k. And the expected time between successive returns to state j is given by wj bar is equal to sum over k pi k over nu k divided by pi j, which is equal to 1 over pj nu j. Further, the limiting rate at which transitions take place is given by limit t tending to infinity mi of t over t is equal to 1 over sum over k pi k over nu k with probability 1. All right. So, we are finding a number of answers here. Of course, the steady state probability, this we already encountered. I mean, we have to prove it, but this answer we already knew. This is expected wjj or wj bar, and this is the rate at which the process makes transitions. There is a for every CTMC there is an average rate at which the transitions take place, and that is given by 1 over sum over k pi k over nu k. All right.